Hi, this is Professor Sartor, and I'm going to be working a few more problems related to exponential and logarithmic functions. This question says, use the properties of logarithms and the logarithm property of equality to solve the logarithmic equation. Let's focus on this logarithmic property of equality. What this property says is if you have the situation where you have log base b of m equals log base b of n, focusing on the details here, we have an equation in which on both sides we have a log with the same base. So if we have this situation, this property tells us that what's inside the logs must be equal to each other. So therefore m must equal n. If we look at the problem that we were given, log base 3 of 2x plus 3 equals log base 3 of 13, we have exactly that situation where we have an equation, and on both sides of that equation we have log base 3 and log base 3. And so this property tells us that what's inside the logs must be equal to each other. So this property allows us to simplify the equation. So we started off with log base 3 of 2x plus 3 equals log base 3 of 13. And that property says that what's inside the log on the left has to equal what's inside the log on the right, giving you a simpler equation that doesn't have logs in it. Then we're going to solve this equation by getting x by itself. So we'll subtract 3. That gives me 2x equals 10. We'll divide both sides by 2, and we get x equals 5. Every time you solve a log equation, you must check your work. And that's because log equations have domain restrictions. You can only take the log of positive values. So we need to make sure that when we substitute that x equals 5 into our equation, that we're going to get log of a positive value. So I'm substituting the 5 in for x, and simplifying, that gives me 10 plus 3 and log base 3 of 13. So as long as what's inside my log comes out to be a positive value, I'm going to keep that solution of x equals 5. If I get a negative value inside the log, then I have to throw that solution away. This question says, use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. So the logarithmic property of equality says if you have log base b of m equals log base b of n, then m equals n. So in order to use this property, I need an equation where we have log base b and log base b, so the same base on both sides. When I look at the equation that I have natural log 4 plus natural log x equals natural log 6 plus natural log of 3x minus 3. The equation that we have doesn't fit this logarithm property of equality right now because I have multiple logs on this side and multiple logs on this side. So before I try to use that logarithm property of equality, I need to use some other properties of logarithms to condense each side of the equation to be a single log. So on the left, I have natural log 4 plus natural log x. One of the properties of logarithms is called the product rule. You're able to, with the product rule, condense these logs into multiplication. So because we have both logs being the same base, these are natural log, which is base e, and we're adding, that can condense to having a product. The same thing can happen on the other side of the equation. We have natural log 6 plus natural log of 3x minus 3. We have the same logs. Both of these are natural logs, base e, with a sum. So we're able to condense this to a single log, and it becomes 6 times 3x minus 3 inside that natural log. So once we've condensed both sides of the equation, we now have it in the right format to be able to use this logarithm property of equality. On the left, we have natural log. On the right, we have natural log. So what's inside these logs must be equal to each other. So that's going to give me 4x equals 6 times 3x minus 3. I'll use the distributive property to give me 18x minus 18. I'm going to move all the x's to the same side of the equation. It gives me negative 14x equals negative 18. Divide both sides by negative 14, and I get x equals 18 over 14, and negative divided by negative is a positive, and this reduces down to 9 over 7. Every log equation needs to be checked. You're checking to make sure that you have a positive inside the log. So when we check, we have natural log 4 plus natural log of 9/7 equals natural log 6 plus natural log of 3 times 9/7 minus 3. So because we have log of a positive here, that's okay. In this term, 3 times 9 would be 27 over 7 minus 3. 27 over 7 is a little bit more than 3. So a little bit more than 3 minus 3 is also going to give you a positive value inside that log. So we're going to keep that solution of 9 over 7 as our answer. This question says solve the logarithmic equation. The equation is log base 3 of x squared minus 16 equals log base 3 of 6x. So we're going to use the logarithmic property of equality. So because we have log with the same base on both sides of the equation, we're able to say that what's inside each of these logs have to equal each other. So that simplifies our equation to be x squared minus 16 equals 6x. This is a quadratic equation, so I'll move all the terms to the same side, giving me x squared minus 6x minus 16 equals 0. I'm going to solve by factoring. This term times this term needs to equal x squared, so that's going to be x and x. This term times this term needs to equal 16, so I need to choose factors of 16. So that could be 8 and 2, and 8 and 2 could give me the correct middle term. I need a minus 8 and a plus 2. Once I have it factored, I'm going to set each factor equal to 0, and that gives me x equals 8 and x equals negative 2. Once I get these answers, I need to check to make sure that we're not taking the log of a negative value or the log of 0. So let's check x equals 8. For x equals 8, that would give me log base 3 of 8 squared minus 16 equals log base 3 of 6 times 8. And this is 64 minus 16, which is a positive. And 6 times 8 would be 48, which is a positive. So we're going to be able to keep that answer of x equals 8. Let's check x equals negative 2. Log base 3 of negative 2 squared minus 16 and log base 3 of 6 times negative 2. So this gives me 4 minus 16. That's going to come out to be a negative, and you cannot take the log of negative. It's undefined. So we're going to have to throw away that answer. So the only solution is going to be 8. X equals 8. This question says solve the logarithmic equation. Our equation is log base x divided by 5 of 4 equals 2. In this example, we can't use the logarithmic property of equality because I don't have a log on the right-hand side. So I'm going to use a different idea, which is to convert this logarithmic equation to an exponential equation. So to convert it to an exponential equation, I need the base of the log. The base of the log is going to be the base of the exponential. Then the log always equals the exponent, so this value of 2 will be the exponent. And then what's inside the log is what the exponential equals. So that's going to equal 4. So that gives me my equation, x over 5 squared equals 4. I can simplify by applying the exponent. That's x squared over 25 equals 4. I'm going to get rid of the denominator by clearing fractions. It's multiplying 25 onto both sides. And I've got x squared equals 100. And I can square root both sides. The square root and the square cancel each other out, and I get a plus or minus symbol on the other side. Square root of 100 is 10. I need to check my work. I need to check x equals 10. I've got log of 10 over 5 of 4 equals 2. 10 over 5 would be a base of 2. And a base of 2 is a valid base. Your base, if you have log base b of x, your base is only allowed to be certain values. Your base needs to be greater than 0 and not equal to 1. And so a base of 2 is a valid base for the logarithm. And then we're going to check x equals negative 10. That would give me log of negative 10 over 2. Sorry, that's a 5. Log of negative 10 over 5 of 4 equals 2. That would give me log with a base of negative 2. Having a negative value for a base is not valid, so we cannot keep this solution. So the only solution we're going to have is 10. This question says solve the logarithmic equation log base 5 of 6x plus 1 minus log base 5 of x minus 6 equals 2. So there are two methods for solving these logarithmic equations. The logarithmic property of equality, and in order to use that property, you have to have logs on both sides of your equation. We don't have that. The other method is to convert it to an exponential, and for that method you need to have a single log on one side of the equation. So I could do that, but first I would need to condense these logs together using the quotient rule. So I'm going to start by copying my question log base 5 of 6x plus 1 minus log base 5 of x minus 6. And the first thing I'm going to do is condense to a single log. I'm allowed to condense to a single log because these logs have the same base. And because I'm subtracting them, I'm using the quotient rule. This log, which is positive, will go into the numerator. And this log that is negative will go into the denominator. The right-hand side of the equation hasn't changed. So now I've condensed to a single log, and I can now convert this log equation into an exponential equation. The base of the log is the base of the exponent, so we're going to have a base 5. The log always equals the exponent, so we're going to have an exponent of 2. And my exponential always equals what's inside the log. So this side is what's inside the log. 6x plus 1 over x minus 6. So my equation, my exponential equation, is now 5 squared equals 6x plus 1 over x minus 6. Now I'll start solving. 5 squared is 25 equals 6x plus 1 over x minus 6. I need to get rid of the fractions, so I'm going to multiply both sides by the denominator of x minus 6. That gives me 25x minus 150 equals 6x plus 1, because these guys cancel out. I want to move all the x's to the same side, so I'm going to subtract 6x. That gives me 19x minus 150 equals 1. I'm going to add 150 to both sides. That gives me 19x equals 151. I'll divide both sides by 19. And since that can't be reduced, we'll leave that as 151 over 19. Then we need to check. We're going to check log base 5 of 6 times 151 over 19 plus 1. That's going to be positive. This is a positive times a positive. That's a positive plus a positive is a positive. All right, then we need to check the other log. Log base 5 of 151 over 19 minus 6. So all I need to do is see if 151 over 19 is greater than 6. And that is about 7.9. 7.9 minus 6 would come out to be a positive. So we're going to be able to keep this value. So that would be my solution, 151 over 19. This question says solve the exponential equation e to the x equals 3. So there are 3 methods for solving exponential equations, 3 basic methods. And the first one is relating the bases. In order to do relating the bases, you have to be able to write the equation as b to the x equals b to the y. And what that means is that the bases need to be the same on both sides of the equation. We're not able to change that 3 to have an e to a power without maybe a calculator. So we're not going to use relating the bases. Then there are 2 other methods that I use typically, and that is to take the log of both sides or to convert to a log. And either one of those methods will work on this example. So I'll show you both. So for method 2, which is to take the log of both sides, you would start off with e to the x equals 3. And you'll take the log. Now, you can use any log you want, but typically people will use natural log or the common log, which is base 10, because those are easily available on calculators. Other log bases are not as easily available. So I'm going to use natural log on the left and natural log on the right. So you take the log of both sides. And once you do that, then inside this left-hand side, you have something to a power. And that means you can use the power rule. And the power rule allows you to pull that exponent in front. And it gets the variable out of the exponent. Then we want to simplify natural log of e. Natural log of e is equal to 1. Let's talk about that for a second, how we know that. Natural log e is the same thing as log base e. Log base e of e. And when the base of the log and what you're taking the log of are the same, that's equal to 1. If I rewrite this, it might make a little bit more sense. The base is e. The power is 1. And then that equals what's inside the log. So we're able to simplify natural log of e to be 1. And 1 times anything is itself, so we have x equals natural log 3. So I'm going to continue with my calculator since this question asks me to round 4 decimal places as needed. So I'm going to type in my calculator natural log 3 and enter. And so x is approximately 1.0986. So I mentioned that we could also use the method of converting to an exponential. So let's think about that. Converting to a logarithm. So let's think about that approach. If you have e to the x equals 3, and you want to convert that to a logarithm, you would write the word log, and the base that you're going to use is the base of your exponential. So I would use a base of e. Then your log always equals the exponent. So that log is always going to equal the exponent, which is x. And then what's inside the log is what your exponential equals. So I was able to rewrite that exponential equation in log form. Now we don't typically write log base e. We have special notation, which is natural log. So it's natural log 3 equals x. And you can see we got the same answer that we got before. X equals natural log 3. So typing that in our calculator, we got approximately 1.0986. This question says solve the exponential equation 2.65 to the x equals square root 7 to the 1 minus 4x. So in this question, we can't use relating the bases to make our bases the same on both sides. So what we're going to do is take the log of both sides. So let me write the original question. 2.65 to the x equals square root 7 to the 1 minus 4x. I'm going to take the log of both sides. That's natural log of 2.65 to the x, natural log of square root 7 to the 1 minus 4x. And now because we've introduced the log into our equation, we can use the power rule. The power rule allows us to take these powers in front of the log, and it takes the variable out of the exponent. So using the power rule, we get x times natural log of 2.65 equals 1 minus 4x times natural log square root 7. Then on the right side, I'm going to use the distributive property. I'm going to take this natural log square root of 7 and distribute it to each term. That gives me x natural log 2x plus 6, x times natural log of 2.65 equals natural log square root 7 minus 4x natural log square root 7. So now I notice that I've got an x in this term and an x in this term. In order to get x by itself, I need to have all the x's together first. So I want to move this term, negative 4x natural log square root 7, to the other side of the equation. So I'm adding that to both sides. So it'll cancel out from the right-hand side. So it cancels out from the right-hand side. The only thing left on the right will be natural log square root of 7. And on the left, these are not like terms, so I'm not able to combine them together. So I'm just going to write it down. X natural log of 2.65 plus 4x natural log square root of 7. Now that I've got the x's on the same side, I'm going to factor that x out. So now I have natural log of 2.65 plus 4 natural log square root of 7 equals natural log square root of x. And now that I have x by itself, I'm able to divide both sides by what's in the brackets. So I have x times what's in the brackets, natural log 2.65 plus 4 natural log square root 7 equals natural log square root 7. I'm going to divide both sides by natural log 2.65 plus 4 natural log square root 7, doing the same thing on both sides. And I get x equals natural log square root 7 over natural log 2.65 plus 4 natural log square root 7. Now my directions here say to round to 4 decimal places. So let me get my calculator and try to type this out. So I'm going to type natural log square root 7 divided by, I need parentheses around my denominator, natural log of 2.65 plus 4 natural log square root 7, close parentheses. Well, let me delete that. I want to move my arrow. Oops. Let's delete. Move my arrow to close parentheses for the log and close my parentheses for the denominator. And I have approximately negative 0.6093 4 if I round to 4 decimal places. So that would be my answer for that question. This question says, how long will it take an investment to triple if it is compounded continuously at 14%? So first I want to pay attention to this part where it says compounded continuously. That's going to tell us to use the formula A equals P e to the RT. That's our compound interest formula when it's compounded continuously. This value of 14%, that's going to tell us our interest rate is 14%, and we'll write that in decimal form, which is 0.14. And it says how long in our question, which means that we're looking for the time. That is our unknown. So looking at my formula again, we are looking for time, so that's my question mark. We were given the interest rate, but I don't see any other real numbers in this problem. But the thing to pay attention to is that this question is asking when this investment will triple. That doesn't give you an exact number, but that does tell you the relationship between the amount you start with and the amount you end with. And the amount you start with is your P, your principal, and the amount you end with is A. So since we're talking about tripling what I started with, I know that my ending amount will be 3 times my starting amount. So even though we weren't given these numbers exactly, we're going to be able to use this idea of tripling what we started with to be able to solve this question. So my formula, A equals P e to the RT, I'm going to change the A to 3P to represent tripling what I started with. The P I'm going to leave alone. I'll substitute in for R 14%, 0.14, and T is my unknown value. Now my goal is to solve for T. I want T by itself. In order to solve, I'm going to get rid of that P by dividing both sides by P. That cancels out P on the left, and it also cancels out P on the right. So even though we don't know the starting amount, we don't need it. Then I'm going to continue to solve by taking the log of both sides. I'll take the natural log on the left and the natural log on the right. On the right, I'm able to use the power rule and bring that 0.14t in front of natural log e. Natural log e is equal to 1. And natural log 3 equals 0.14t. I'm going to divide both sides by 0.14, and I get t equals natural log 3 over 0.14. So let's type that in our calculator. Natural log 3 divided by 0.14. So that gives me 7.847. And if I read the directions up here, it says to round to 2 decimal places as needed. So I would use 7.85 when I round to 2 decimal places. This question says the population of Adamsville grew from 6,000 to 14,000 in 5 years. Assuming uninhibited exponential growth, what is the expected population in additional 5 years? So we're going to be using this formula for population growth, the uninhibited exponential growth, that looks like this. P of t equals P0 e to the kt. So make sure we understand the parts of this for a second. This P0 or P0 That's going to stand for our starting population or initial population. The K is our growth or decay rate. And because this population grew from 6,000 to 14,000, I know it's going to be growth, and I know that value is going to be positive. Then we have T, which is time. It looks like this problem is dealing with years, so it'll be time in years. And this P of T, this is going to be the amount of the population after a certain period of time. The population after T time. So, looking at our problem again, just want to read over it one more time. We have that the population grew from 6,000 to 14,000 in 5 years. So we start with 6,000, and since we're starting with 6,000, that's going to be our P naught, our initial population. And then if we grow to 14,000 in 5 years, we have a time of 5 years, and we get to a new population, P of 5, and that new population is 14,000. So I'm going to be able to use those pieces of information in order to find the growth rate. So let's do that. We take our formula, P of T equals P naught e to the kt, and in for P of T, that's going to be P of 5, that's 14,000 equals 6,000 e to the k, I don't know k right now, but t is 5 years. Then I can divide both sides by 6,000, and that would reduce to 14 over 6. The 6,000s cancel from the right, giving me e to the 5k. 14 over 6 reduces down to 7 over 3. And then I can solve this exponential equation by taking the log of both sides. I'm taking the natural log of both sides. Because I've introduced the log, now I can use the power rule and bring this power out front. It's 5k natural log e. Natural log e is equal to 1. So that's 5k times 1, which is just 5k. And I can divide both sides by 5. And now I have k, the growth rate, natural log of 7/3 over 5. Now you could put this in your calculator and get a decimal answer, but I don't want to round until the very end of the problem. And you can see even the directions here, it says do not round into the final answer. So I'm going to leave this alone for the moment. Now I'm going to erase this, and let's read the question again to make sure that we answer what's being asked. So in this question, it wants us to find what is the expected population in an additional 5 years. So we've been able to find our growth rate, and now we can modify our formula to be specific for this problem. We know that P naught was 6,000, that's our initial population. And we know the growth rate now is natural log of 7/3 over 5. And so now if any moment of time, I can find the population of this. So this says an additional 5 years. So we had 5 years to get to 14,000. We want to know the population in another 5 years. So that's going to be 10 years. So we want to do P of 10. So that's 6,000 e to the natural log of 7/3 over 5 times 10. I'll type that in my calculator to see what I get. We want to round to the nearest whole number. So in my calculator, I'm going to type 6,000 e, and I like to put the 10 in the front, times natural log of 7/3, close parentheses for the log, and divide by 5. So that gives me 32,666.6. We want to round to the nearest whole number. That's 32,667. So another 10 years, our population grows to 32,677. This question says, a certain radioactive isotope is a byproduct of some nuclear reactors. Due to an explosion, a nuclear reactor experiences a massive leak of this radioactive isotope. Fortunately, this isotope has a very short half-life of 14 days. Estimate the percentage of the original amount of this isotope released by the explosion that remains 9 days after the explosion. Now that's a lot of information to take in. So let's start with what formula we're going to use. So the formula that we're going to use for this problem is A of t equals A naught e to the kt. So this is the formula, and the parts of the formula, we have the A naught. This is going to be our initial amount, our starting amount of this isotope. The K is going to be our growth or decay rate. And because we're talking about the isotope having a half-life and how much of it remains after 9 days, this is going to be a decay rate, and this value will come out to be negative. So because it has a half-life, it's decaying instead of growing, and we'll have a negative value of K. Then we have our T, which is in time, and looking at our problem, we're dealing in days. So T is time in days. And then our A of t is our ending amount of this isotope. A of t is the amount after t days. Okay, so now that I think you're a little bit more comfortable with the formula, this question really needs to be done in 2 parts. This information about having a half-life of 14 days is going to help us find this K value, the decay rate. And then after we find that decay rate, then we're going to be able to answer this question that's being asked. So we're going to ignore this information about 9 days after the explosion until we figured out the value of K. So it says we have a half-life of 14 days. Now I think it's pretty obvious that 14 days is referring to the time. But this half-life is the amount of time it takes to decay to half of what you start with. So this is really telling us the relationship between the starting amount of the isotope and the ending amount of the isotope. So this is saying that it takes 14 days to decay to half of what you started with. So for example, if you started with, say 100 of the isotope, then after 14 days, you would then have 50 left. So it's telling you that relationship between the initial amount and the ending amount. So that is going to be A equals 1/2 of A naught, half of what we started for half-life. So we're going to take our formula, A of t equals A naught e to the kt, and substitute these two pieces of information into that formula. Having a half-life means that my A of t is going to be half of my starting amount and a time of 14 days. Now we're going to be able to solve for that value of k, the decay rate. We're going to solve by dividing by A naught on both sides. That gives me 1/2 on the left and e to the 14k on the right. Then I'll take the log of both sides to solve this exponential equation. I can use the power rule to bring that 14k out front. Natural log of e is 1. So that gives me 14k. I'll divide both sides by 14, and I get k equals natural log 1/2 over 14. So now I have my decay rate. And now I'm going to be able to answer this question that they ask. Estimate the percentage of the original amount released that remains 9 days after the explosion. So my model started off being A of t equals A naught e to the kt. And now that I've figured out that now that I've figured out the decay rate, I can substitute that in. I could put that in my calculator right now, but I don't want to round too soon. So I'm going to leave it in that messy symbols so that it's exact and not rounded. So we want to know how much is remaining 9 days after the explosion. So we're going to substitute a 9 in for t. So A of 9 equals A naught e to the natural log 1/2 over 14 times 9. We're going to put that in the calculator. That's e. I'm going to put the 9 in front. E to the 9 times natural log. I will type 0.5 instead of 1/2. Close parentheses for the log and divide by 14. So that's going to give me A of 9 equals A naught times 0.64. And if we go back and read this question one more time, it says we want to write our answer as a percentage, and we want to round to the nearest whole number for our percentage. So we got 0.64. We'll move that decimal place over 2 to turn it to a percentage, and that's 64%. 64% will remain 9 days after the explosion.